If I can't picture it, I can't understand it. Albert Einstein. Welcome, students. In the last lecture of methods of impulse and momentum, we have talked about conservation of linear momentum. And we have tried to understand its application on very simple examples. The principle states that if there are no external forces or there is no net external force, total linear momentum of a system remains conserved. This principle involves both the quantities, forces and momentum as vectors. So the idea can be implemented for a particular direction also. That is, if in a particular direction there is no net external force or there are no external forces, total linear momentum component of system in that direction will remain conserved. We also try to understand the idea, that is, principle of conservation of momentum, with the help of impulse momentum principle, and we came about a very important conclusion about impulse events like explosion or something. In impulsive event, even if there are external forces present and they are finite, in such cases, total linear momentum of such events can be assumed almost conserved. Say, a shell explodes in air, gravity is acting, air resistance is acting, but duration of explosion is infinitely small. So in that duration, impulse of gravity and impulse of air resistance will become negligible as compared to impulses of internal forces. So the impulses of gravity and air resistance being negligible can affect total momentum system by a negligible amount. So total momentum of the shell for the explosion can be assumed almost conserved or fairly conserved for all practical purpose. Today in this lecture, we discuss about some advanced level examples, say part B, advanced level examples. You can see on this diagram, there is a wedge and here is a block. If the block is released on the wedge and if there are no friction, the wedge will slide in this way and the block will slide in this way. How their velocities are related, such kind of situation we try to explore today lecture. So let us come on example 9. That number is in continuation with the last lecture. Say here you can see in the figure there is a cart which can travel or move on a straight horizontal track, and a ball is suspended from a fixed point in the cart with the help of a thread that is inextensible. Let us see what other parameters are given. A ball of mass mb is suspended from a cord of length L attached to a cart of mass mc that can move on a horizontal frictionless track. If the ball is given an initial velocity ub at its lowest point, how much high will it swing? Say here ball is given this velocity ub when it is at lowest point. So the ball will proceed forward. As the ball proceeds forward, this thread will tilt and the tension forces of the thread will act at this point on the cart, and its horizontal component will cause the cart to move also forward. But during this process, the ball will swing to a height and return back. So we have to calculate up to what maximum height the ball has to swing. Now how we can proceed? When the ball reaches the maximum height h, the velocity of the ball relative to the cart becomes zero. Thus, both have the same horizontal velocity, say v. That is very important idea. Say, you can understand it or you can simply visualize it. When the ball reaches its maximum height, extreme point of the swing, at that time, velocity of the ball with respect to cart will become zero, or we can say cart and the ball both will have the same velocity, and we are assuming this velocity to be v, and the height to which the ball swings by h. And for these two situations, initial situation and final, when the ball is at maximum height, we can apply conservation of momentum in horizontal direction. Due to absence of external forces in the horizontal direction, the horizontal component of momentum of the system, ball cart system, remains conserved. And we can think here, say initial position, when the ball is given velocity, at the time the cart is at rest, And finally, when the ball will swing to its maximum height, say h, both will have same velocity. And we are assuming here y and x, y vertical, x horizontal. So we assume conservation of momentum in x direction because in horizontal direction there are no external forces on the system. Applying principle of conservation of momentum for horizontal components, we get the idea is summation pix is equal to summation pfx. Here I and f denotes initial and final situations, and here summation denotes total momentum component of the entire system. So what we can write here, initial momentum is the mass of the ball into velocity of the ball. So it will be mbub, and finally final momentum is mass of the cart into velocity of the cart plus mass of the ball into velocity of the ball, and both have the same velocity. So what is the final momentum? mbv plus mcv. So here mbub is equal to mbv plus mcv. Here we are not interested in this quantity v. We are interested what? Up to what maximum height the ball will swing. So here we know that velocity of the ball has changed from ub to v over a displacement. So it is the area of use of energy methods. So we'll apply work energy method to determine the height h. We should apply the work energy theorem on the ball cart system. For that, we calculate the initial and final kinetic energies, and we see all the work by all the internal and external forces, and then substitute these expressions what we get in the work energy theorem. So let us first determine initial and final kinetic energies. Initial and final kinetic energies. Initial kinetic energy is the only kinetic energy of the ball, that is half mbub square. So summation k initial equal to half mbub square and plus 0 because cart has no kinetic energy initially. And what is final kinetic energy? Final kinetic energy is kinetic energy of the cart plus kinetic energy of the ball. So we can add kinetic energy of both the things and substitute v from here, or we can use, because finally there is no relative motion between cart and the ball, so both are moving as a single rigid body, so we can use here p square by twice of m. So let us write here final kinetic energy, summation k final is equal to summation p final x square upon twice of total mass. So we are using this idea, and final momentum is again equal to initial momentum. So summation p ix square upon twice of total mass, because this we can write from conservation momentum. So let us substitute value of initial momentum mbub. So what is summation k final? mbub whole square upon twice of mb plus mc. So we have written both the kinetic energies, initial and final. Now we see work done by various forces. Forces of gravity on the cart and the ball, and forces of normal reaction on the wheels of the cart are external forces on the system. The tensile force in the string at the cart and at the ball are the internal forces. So let us see what are the external forces and what are the internal forces. Force of gravity, that is weight of the ball. Force of gravity on the cart, that is weight of the cart. And normal reaction forces on each wheel, every wheel of the cart are the external forces. And tensile force, tension T acting here on the cart and tension T acting here on the ball. These two are the internal forces. Work done by various forces. So let us see which of these forces will do work and what will be their expressions. Only the external force of gravity on the ball does work. Work of gravity on the cart is 0, as displacement of the cart and the force are perpendicular. Work of the normal reaction on the wheel is 0, as the particle of the wheels on which normal reaction act has 0 velocity. Here, this is very important idea. Why work done by gravity on the cart is 0? Because force of gravity on the cart and displacement of the cart are in perpendicular direction. But why work done by normal reaction on the wheel are 0? Because when the cart is moving, point of contact the wheel on the track on the ground will be at rest. So power of normal action will be 0. That's why total work done by normal action is 0. Here sometimes I have seen the students are committing mistakes in understanding that, because they say yes, displacement is perpendicular to normal action, so work done by normal action will be 0. But that is not the idea. What is the idea? Actually, the points or the particles of the body on which normal reactions forces are acting, they are stationary with respect to ground. That's why their power is 0. So their work done will be 0. And we can write here the work done by gravity on the ball. So it will be gravity is acting mg downward, and displacement component in the direction of gravity is h upward. So work done by gravity on the ball will be minus mbgh, and that is the total work done by all the external forces. As the string is light and inaccessible, it cannot store mechanical energy. Hence, total work done by the tensile forces on the cart and on the ball must be 0. That is another very important idea. Actually, work is transfer of mechanical energy. The string is light, so it cannot store kinetic energy. It is inaccessible, so it cannot store elastic potential energy. So a string as a whole cannot give mechanical energy to the system or can take mechanical energy from the system. So total work done by both the tensile forces on the system must be 0. Now we write total external work done and total internal work done. Wg is equal to minus mbgh, that is work done by gravity. Wn is equal to 0, and W tensile force is 0, total work done. So what we can write here, summation W external is equal to W gravity plus W normal, that is minus mbgh. So that is work done by all the external forces minus mbgh, and summation W internal will be 0 because the internal forces are tensile forces and their work done is 0. And we have obtained expressions for initial kinetic energy system, final kinetic energy system, work done by all the external forces, and work done by all the internal forces. All these expressions now we have to substitute in the statement of work energy theorem. Substituting the expression for kinetic energies and work in the work energy theorem, we first write the statement for work energy theorem, that is summation W external plus summation W internal is equal to summation K final minus summation K initial. This is work done by all the external forces on the system, that is work done by all the internal forces of the system, that is total kinetic energy system in final configuration, and this is total kinetic energy system in the initial configuration. For summation W external we have minus mbgh, summation W internal 0, summation K final is we have obtained earlier, initial momentum is square upon twice of mass, that is mb ub whole square upon twice of mb plus mc, and summation K initial is the initial kinetic energy given to the ball, that is half mb ub square. Substituting this, what we get, minus mbgh plus 0 is equal to mb ub whole square upon twice of mb plus mc minus half mb ub square. Just by a little bit solving, we get mgh is equal to mb mc ub square upon twice of mb plus mc, and we cancel mb and mb, bring g from here to here. What we get then, h is equal to mc ub square upon 2g mb plus mc. So in this way we have calculated the maximum height to which the ball will swing in the n-swing motion. Now let us come on the next example and we try to understand some more details of momentum conservation and application of work energy theorem on a system from that example. Example 10. The setup is given here. That is the same setup what we had described on the beginning screen. Here there is a wedge that is placed on horizontal floor. When the block is released here, the block slides down the wedge and the wedge will move here. Now what is the problem? A small block of mass small m is released on the top of a stationary wedge of mass capital M that can slide on a horizontal floor. Assuming all surfaces in contact to be frictionless, calculate the velocity of the wedge when the block has descends a height h. At first sight, it seems that there are three unknown. One is the velocity of the wedge, because direction is known, so we have only one unknown, its magnitude, and direction of velocity of the block is unknown. So here we have two unknown regarding the block, its velocity, magnitude, and direction. But by using relative motion idea, we can reduce these three unknown to two unknowns. How? Let us assume velocity of the wedge to be v, and velocity of block related to wedge, that will be in this direction, to be u. So block with this wedge will carry the block here in this direction. So velocity of block related to ground will be vector sum of u and v. Now let us see how we realize this idea. As the block slides down the wedge slides towards the left and simultaneously carries the block, denoting the velocity of the block relative to the wedge by u and velocity of the wedge relative to the ground by v. Velocity of the block related to the ground, say ub, is shown here in the diagram. Just see, we have shown the block has descended some height. Let us see, its velocity is u, that is related to the wedge because it's sliding velocity, and velocity of the wedge we have in v, so it will carry the block also with velocity v. Now vector sum of u and v will be the velocity of the block with respect to ground, say ub, in this way. Now in this way we have to determine only two unknowns, v and u, and these two unknowns can easily be determined by making two independent equations. One is from conservation of linear momentum in horizontal direction, because there are no external forces on the system in horizontal direction, and second by using work energy theorem. The velocities can easily be determined using principle of conservation of momentum and work energy theorem, together with the above relation or relative motion idea. If you implementing this relative motion idea, these velocities can be determined. Why I am saying that a relative motion idea? Because to write kinetic energy of the block, we must need ub, because that will be half mv ub square. Now just see, conservation of momentum due to absence of horizontal external forces on the block wedge system, horizontal component of total momentum of the system remains conserved. So what equation we can write here? Initially the momentum was 0, so we have shown everything is motionless. Now just see, the block has descended some height here, so it has velocity u related to wedge, velocity of wedge, so this velocity of the wedge is added here. Now we can write conservation of momentum in x direction. So what the statement of conservation of momentum? Summation pix is equal to summation p final x. So initial momentum was 0, is equal to minus mv minus mu plus mu cos theta. Just see here, minus mv plus m into minus v plus u cos theta, and just by this equation what you get, mu cos theta is equal to m plus capital M into v. So we have this equation, say equation number 1. Now we have to write equation of that is obtained from work energy theorem. For that we have to determine initial and final kinetic energy of the system, and work done by all the external forces and work done by all the internal forces. So let us see here, work energy theorem. Initial and the final kinetic energies of the system. Initial kinetic energy is of course 0, because everything was motionless. And what will be final kinetic energy? Let us see here. K initial is equal to 0. What is K final? Half mv square plus half m u square plus v square plus 2 uv cos pi minus theta. If you recall the diagram, angle between u and v was pi minus theta. So just by solving this, what you get? Half mv square plus half small m u square plus v square minus 2 uv cos theta. So in this way, we have written the final kinetic energy of the system. Now we write work done by various forces. So here, that is, it has descent height h, velocity v, and velocity u, v. So in this way, you can write the kinetic energy. And let us see the forces acting on it. Mg, that is external force, weight of the wedge, small mg, weight of the block, and normal action from the ground. These are the external forces. And out of these external forces, work done by mg will be 0 because displacement of the block is perpendicular to mg. And similarly, normal direction of the ground is 0 because the particle on which normal direction is acting are moving towards the left, so their displacement is perpendicular to normal direction. Why I have said particles on which normal direction are acting? Actually, the normal direction we have shown here, a mathematical equivalent by resultant, but this normal direction is distributed force. Similarly for mg, but at present here we are showing them by a resultant force. Only this small mg is doing work. So work done by small mg is mgh because h is in the direction of mg. So only the force of gravity on the block does work as an external force. Other external forces, force of gravity on the wedge and the normal reaction on the wedge from the floor do no work as displacement of particles on which they act are perpendicular to the forces or to the respective forces. So what we can write from here, summation W external is equal to mgh. Total work done by the internal forces, the normal reaction between the block and wedge, and the is 0. That is also 0. So summation W external is equal to small mgh and summation W internal is equal to 0. Now we have all the things to substitute in work energy theorem. Initial kinetic energy, final kinetic energy of system, summation W external and summation W internal. Substituting these expressions of kinetic energies and work in the work energy theorem, we get, so first we write the work energy theorem, summation W external plus summation W internal is equal to summation K final minus summation K initial. So in place of this, what we write, small mgh, it is 0, small mgh plus 0 here, half mv square plus half m u square plus v square minus 2 uv cos theta, and for this we have minus 0 because initial kinetic system is 0. And by solving this equation, what we get, mgh is equal to half mv square plus half m u square plus v square minus 2 uv cos theta. So we have just removed 0, and further simplification we do whenever required. Substituting expression for u obtained from equation 1 in the above equation, what we get? Actually, we have to find v. So from this equation, we have to eliminate u. So from equation 1, we substitute u. So we get here v is equal to 2m square gh cos square theta upon in bracket m plus n, and again in bracket m plus m sin square theta. So that is velocity of the wedge. Now here one thing you have to take down, just note here, that is instead of assuming velocity of the block with respect to ground, what we have done, we have make use of relative motion idea. Sometimes you may think that in place of u and v, we can assume x and y component of velocity of the block. Again, if you assume x and y component of velocity of the block with this ground, you will have 3 unknowns, so you have to make 3 equations. So again, it will become somewhat more cumbersome. So I suggest to you that whenever you have this kind of thing, really, whenever you have chance to use a relative motion idea, use it. Now we proceed on the next example. Example 11. Just see here, on a frictionless floor, we have a block of mass capital M. It is attached with a light spring of force constant K, and here is a block of small m that is rushing toward the spring with the velocity u. So what we have to calculate here, a block of mass small m sliding with the velocity u on a frictionless floor collides a light spring of force constant K. The other end of the spring is attached to another block of mass capital M, as shown here. Now what is asked? Part A, determine the maximum compression of the spring in the ensuing motion. Now this problem is similar to the problem what we had in cart and ball. In cart and ball problem, what was there? When the ball has swung to its extreme position, maximum height, at that time velocity of ball and cart was the same. And then we have used for that momentum conservation. And then to find h, we have used work energy theorem. Here we do the same thing. The only difference is that in that problem, external force, weight of the ball was doing work and no internal force was doing work. But in this situation, there is no external force which do work. this internal force of the spring will do work. And again, when the spring compression will be maximum, at that instant, velocity of this block and this block will be the same. So how we proceed? Due to absence of horizontal external forces on the system or a spring block system, the total momentum being in the horizontal direction will remain conserved. Here we will not, you can say the horizontal component momentum will remain conserved. But here the total momentum system is in horizontal direction. So we can say the total momentum is conserved. So in addition, at the time of maximum compression in the spring, both the blocks have the same velocity. And let us denote that velocity by V. So denoting velocity of the blocks at the time of maximum compression in the spring by V, momenta of the system are shown here. Initially, this mu, it has only this momenta, and this has no momentum, and xy coordinate equal to, both will have same velocity, so its momentum is mv, this momentum is capital MV. So by conservation of momentum, what we can write here? Applying conservation of momentum, we get summation pix is equal to summation p final x. So what we have, mu is equal to mv plus capital MV. So let us call equation number 1. Now we are remaining with to write expression for work energy theorem, or just to apply work energy theorem. For that, we need total initial kinetic energy, total final kinetic energy, work done by all the external forces, and work done by all the internal forces. Let us first explore them. To determine the maximum compression, we should now use work energy theorem. Why work energy theorem? Because here velocity changes are involved with some space changes or some displacement. So we use work energy theorem. Work done by various forces. External forces of gravity on the blocks and forces of normal reaction on the blocks from the floor do no work, as displacements of the particles on which these forces act are perpendicular to these forces. So that is a very simple idea. Only the spring force does work as an internal force, denoting the maximum compression by xm. Work of various forces can be expressed as summation W external 0, summation W internal 0, summation W internal is minus half k xm square, because spring is doing work. And how we can write work done by spring force? Initial potential is spring minus final potential is spring. That is work done by spring. So initial potential was 0 and minus potential is stored is half k xm square. So in this way we have minus half k xm square. Initial and the final kinetic energies of the system. So k initial is half small m into u square. And what is k final? That is half small mv square plus half capital MV square. Or you can say here, what half m plus m v square. So substituting the expression for kinetic energy and work in the work energy theorem, what we get? Just see. So let us substitute value. Summation W external plus summation W internal is equal to summation K final minus summation K initial. So W external summation is 0. That is minus half kxm square. 0 minus half kxm square is equal to half m plus m v square minus half mu square. And what we have to do? Kxm square is equal to mu square minus m plus m v square, in this way. Equation number 2. Substituting the expression of velocity v at the time of maximum compression from equation 1 in the above equation, or equation number 2, what we get? Kxm is equal to mu square minus m, this mu upon m plus m square. Now by solving this, what you get? Xm is equal to u mm upon km plus m. So that was again idea. Here one thing we have also simplified here. This kinetic energy, finally, we can write with the idea what? Momentum, initial momentum square upon twice of mass, because momentum is conserved. And at the time of maximum compression, both the blocks have same velocity. So this we could have written very easily what? Small mu whole square upon twice m plus m. In this way, this would have become somewhat simpler. Now just we are coming on the next example. Now just see, let us revise all the ideas what we have done here. Actually, at the time of maximum compression, both the blocks have same velocity. So to find that velocity, we have used momentum conservation, and then we have used work energy theorem to find maximum compression. Now let us come on the part B of this problem. Determine final velocities of both the blocks when all interaction between them ceases. Means actually when block will rush up toward the spring, it will first compress spring, and the compression of spring will become maximum. Then the spring will become relaxed, and after some time the block pressing the spring will be detached, and both blocks will move independently. And we have to find those velocity when the blocks are moving independently, means there is no interaction forces between the blocks. So how we proceed here? Assuming final velocities of the blocks by v1 and v2, both towards the right, we can apply conservation of momentum in horizontal direction, and as there are no external forces on system in the horizontal direction, because just see, in the horizontal direction there is no external force, so horizontal momentum will remain conserved. Actually here total momentum is horizontal, so we can say total momentum conservation we can apply here. Why we are assuming v1 and v2 both towards right? Just to avoid any chance of committing mistake of minus sign. Of course, if any of the velocity has to become reverse, it will come automatically reverse. So here initially that was initial momentum mu, then xy direction equal to final momentum mv1 and mv2, and you can see here no contact between the springs, so there is no interaction between the blocks. So what is the conservation momentum equation? Summation pix is equal to summation p final x. So mu is equal to mv1 plus capital mv2. Let us call equation number 1. Work done by various forces. Actually now we are going to apply the work energy theorem. For that we have to find the work done by various forces and initial and final kinetic energy of system. None of the external force does work. In addition, the spring force, that is an internal force or internal conservative force, also does no work, as in the initial and final situation the spring is relaxed. Thus by applying the work energy theorem, we get, actually here the spring is compressed and then relaxed, and the spring force is conservative, so total work done by spring force is again 0, because again you can see what is the work done by spring, that is the potential energy change in spring. So initial potential spring was 0 and final it is 0. So here, from here we can also say that the spring force is not doing work in this process, net work. So what we get, summation W external plus summation W internal is equal to summation K final minus summation K initial. So 0 plus 0 is equal to half mv1 square plus half mv2 square minus half mu square. So from where what we can write here, mv1 square plus mv2 square plus mu square, say equation number 2. At first sight you see that we'll get here quadratic equation by substituting the values, but a little bit algebraic manipulation will save us from solving quadratic equation. What we are rearranging the terms of these equations, we can write, just see what, say mu minus mv1 is equal to mv2. Just bring it here. Now you can realize the same manipulation we do here and divide. So m and will cancel, and v square minus u square minus v1 square will also get cancelled. So we get u plus v1. So let us see how we get it. So call equation number 1 because it is a modification of equation number 1. And this mu square minus v1 square is equal to mv2 square. Say equation number 2 because it is again rearrangement of terms from equation number 2. Now what we do, dividing the left hand and right hand members of equation 2 with those of equation 1, what we get? Just divide this side by that side. So we get here u plus v1 is equal to v2. So u plus v1 is equal to v2. We So minus v1 plus v2 is equal to u. So we get equation number 3. So by using 1 and 3, we can find v1 and v2 both. From equation 1 and equation 3, we get v1 is equal to u small m minus capital M upon m plus n, and v2 is equal to u 2m upon m plus n. Now you can see it is obvious that v2 must always be towards the right, but v1 may be towards right and v1 may be towards the left, or even v1 may be 0 also. Under what condition? If small m is lighter than capital M, so the direction of motion of the block will reverse after this interaction. If both are equal, then v1 will be 0. If m1 is greater than m, so it will move in the same direction. That's why I have taken this here towards right. So that was again very simple problem. Here I have taken this just to make you the idea of this mathematical idea, because sometimes I have seen the equation students making quadratic equation here and solving them, so it will take more time. So you can use such kind of mathematical manipulations. Example 12. A sleeve of mass m can slide on a frictionless horizontal rod fixed between two rigid supports. A small ball of mass small m is connected with the sleeve with the help of a light inextensible thread of length L. The ball is held, maintaining thread horizontal and straight as shown in the figure, and then release. Just see here. Here is a fixed sleeve, rod, horizontal rod. There is no friction here on the rod, and the sleeve can slide on the rod. Here by an L, a thread is tied, and this thread is attached here to a small ball of mass small m. Initially, the ball is held here and keeping the thread horizontal and straight. Now, as the ball released, what will happen? The ball will move down and the sleeve will move towards the left. So we have to explore this motion. Actually, I will try to just explore various aspects of momentum conservation in this problem. So we take several parts of it here. So what is part A? Find speed of the sleeve when thread has turned through an angle theta. Actually, this problem is similar to the block wedge problem. There, what we have taken idea, just we have avoided 3 unknown, and using relative motion idea, we have reduced number of unknowns to 2. Similarly here, at first sight, regarding velocity, we have 3 unknown, magnitude of velocity of the sleeve and magnitude and direction of velocity of the ball both. So 3 unknown. Just by using relative motion idea, we can avoid these 3 unknown and reduce their number to 2, because with respect to sleeve, the ball will always be in circular motion of radius equal to L and center here. So if we assume velocity of the ball relative to the sleeve, that is V, that is always perpendicular thread. So V, and velocity of sleeve somewhere here. So velocity of ball with respect to ground will be velocity of the ball with respect to sleeve, vector sum with velocity of sleeve. So let us see how we proceed. Kinematics of motion, the relative motion idea, what we discussed, let us try to understand it. Here in this diagram, you can see the thread has turned through angle theta. We assume the velocity of sleeve to be u and u here, and v. This v is made perpendicular thread, so it is velocity of the ball with respect to sleeve, means its velocity of circular motion with respect to sleeve. And the velocity of the ball with respect to ground will be vector sum of u and v. Now you can see about angle. If this angle is theta, this angle will be theta, and this angle is 90. So, and this angle is also 90. So this will be theta. So we have to write first the kinematics. After the ball is released, the sleeve begins to move towards the left due to tensile force of the thread, and the ball on a curvilinear path. Why I am saying curvilinear path? Because with respect to ground, path of the ball will be curvilinear. It will not be a circle. Path of the ball is circle with respect to sleeve. So path of the ball with respect to ground is unknown. But it is known that the path of the ball with respect to sleeve is circle. So we have used here that relative motion idea. Path of the ball relative to the sleeve is a circle of radius equal to the length of the thread, because the distance between the sleeve and the ball is always equal to the length of the thread. Now, that is a very simple idea to understand. Velocity of the sleeve u and that of the ball with respect to the sleeve v are shown here. Velocity of the ball relative to the ground is the vector sum of these two velocities. So that is now we can write what is the velocity of the ball. Velocity vb subscript of the ball related to the ground, that will be vb is equal to, that is this v sine theta minus u whole square plus v cos theta whole square, and by solving this what we get, vb is equal to square root v square plus u square minus 2vu sine theta. So that expression is similar to the block wedge problem. Let us call this equation number 1. Now we come various forces acting. Now let's see various forces, because just exploring the various forces we will be in a position to realize in which direction the momentum will be conserved and how we can apply the work energy theorem. So here forces various are the weights and force of gravity on the ball and the force of gravity on the sleeve. So force of gravity on the ball, force of gravity on the sleeve, and normal reaction by the rod on the sleeve in upward direction. These are the external forces. And tensile force of thread on the sleeve and on the ball are the internal force. That is tensile force of the thread on the ball, that is tensile force of the thread on the sleeve. These two tensions are the internal forces. So we have seen all the forces. Now this diagram is very obvious that there are no external force in the horizontal direction. So total momentum component in the horizontal direction of the system will always remain conserved. External forces on the ball sleeve system are their weights and the normal reaction on the sleeve by the rod. Internal forces are the tensile forces of the thread on the ball and on the sleeve. Now we can apply conservation of horizontal component of momentum because there are no horizontal forces on the system due to absence of external forces on the system in the horizontal direction. Horizontal component of the total momentum of the system remains conserved. So what equation we can write here? This way, this velocity is u, this velocity is u, v. Just we have shown this velocity just to write momentum. That is mg, this is exy. So how we can proceed further? Summation pix is equal to summation p final x. We know that initial momentum was 0 because system was at rest. And final momentum will be minus capital mu minus small mu plus small mv sine theta. So 0 is equal to minus mu minus small mu plus mv sine theta. So this is the momentum conservation equation. So we can rewrite it. M plus mu is equal to small mv sine theta. Let me mark equation number 2. Work energy theorem. How we apply work energy theorem? So for that we must know initial and final kinetic energies and total work done by all the external forces and total work done by all the internal forces. So let us first explore them. Since the situation involves speed change with displacement, energy method should be used to find relation between various speeds and displacements. That's why we are using energy method or work energy theorem. Initial and final kinetic energies. What they are? Initial kinetic system was 0 because system was at rest. So we can write here summation k initial equal to 0. What is summation k final? Half mu square plus half small m vb square. And vb we have obtained earlier in equation number 1, that is u square plus v square minus 2uv cos theta whole square root. So let us substitute the values here. Summation k final half mu square plus half mvb square, that is substituting vb is equal to square root uv square plus u square minus 2uv sine theta. From equation 1 what we get? K final is equal to half mu square plus half mv square plus u square minus 2uv sine theta. So that is final kinetic energy. Work done by various forces. Now we have seen the diagram. What are the various forces? Let us again reproduce the diagram here. that is external force, normal action from the rod, force of gravity of the earth on the sleeve, that is weight of sleeve, and weight of the ball. So out of these, this normal action will not do any work, this mg will not do any work, because displacement of the particles on which these forces are acting are perpendicular to these forces. Only this weight of the ball will do work, and that will be small mg into this displacement L sine theta. Amongst all the external forces, only weight, that is force of gravity of the earth on the ball, does work. Weight of the sleeve and normal reaction on the sleeve, each of these forces do no work, as displacement of the particles on which they act are perpendicular to these forces. So again, one more thing, total work done by this internal force tension is 0. Why? Because the string is light, it cannot store kinetic energy, it is inextensible, it cannot store potential energy. So this string cannot exchange mechanical energy from system, so it cannot do any work. Summation W external is equal to mgl sine theta. The only internal force in the system are the tensile forces in the thread. The thread being light and inextensible, it cannot store mechanical energy. Therefore, total work of the tensile forces is 0. So summation W internal is 0. We obtained initial kinetic energy, we have obtained final kinetic energy, total work done by external forces, and total work done by internal forces. So now it is remaining to substitute this expression in the statement of work energy theorem. Substituting these expressions of kinetic energies and work in the work energy theorem, we get, so let us write the first statement of work energy theorem. Summation W external plus summation W internal is equal to summation K final minus summation K initial. So that is mgl sine theta, that is 0. And so right here mgl sine theta 0, and final kinetic energy half mu square plus half m v square plus u square minus 2 uv sine theta, and this value was 0, so we have not written here minus 0. Now just what we proceed here, let us call equation number 3. Substituting the expression for velocity of the sleeve from equation 2, that is v is equal to m plus mu upon m sine theta, into equation 3, what we get, you can recall here from equation 2 what we get, this v. So u is equal to 2m square gl sine cube theta upon m plus m cos square theta. So that is velocity of the sleeve when the thread has turned through angle theta. So this was the expression. So now let's come on the next part. So we may have used these equations on the next part. So we have written this equation to be 4. B, at which angular displacement of the thread the speed of the sleeve acquired its maximum value. And what is the maximum value? Normally, the maximum value of the speed of sleeve is asked, and by intuitive understanding we can say the sleeve will acquire maximum value when the thread will become vertical. So we'll use that idea, but here we have obtained equation number 4, velocity of the sleeve at every angle of theta. So by substituting angle theta is equal to 90 degree in the equation number 4, we can find that is velocity of the sleeve which is maximum. Why this velocity is maximum? Actually, when the ball is released, the tensile force of the thread on the sleeve is acting towards the left. So it will keep on acting, so it will keep on accelerating the sleeves or increasing its speed till this force vanishes. When this force vanishes, when thread becomes vertical. So till the thread becomes vertical, speed of the sleeve was increasing continuously. So when the thread will become vertical, speed of the sleeve will be maximum. So how we'll proceed by the same idea. Refer the expression for the velocity of the sleeve, that is equation number 4. Here u is equal to 2m square gl sine cube theta upon m plus m, capital M plus m cos square theta. Here we have reproduced equation. From the expression, it is obvious that the speed u of the sleeve will be maximum at theta is equal to 90. the thread, that is the thread become vertical. We can use that intuitive logic also, but if you have expression, you can see mathematically here. All things are constant, only theta is variable. So as theta increases, this will decrease. So denominator will decrease, but numerator will increase. So when theta has maximum value 90, so speed will be maximum. By using theta 90, what we get? Substituting theta equal to 90 degree in the above expression, we get u max is equal to 2m square gl upon m plus m into m. It is very simple. It will become 1. So we like it here 2m square gl. This will remain as it is, but here it will be what? 0. So it will be m because cos 90 is 0. Now we can have another approach. That is, I had told you, that is intuitive approach, because just if this part was asked independently, it was not, you had not arrived at relation earlier. So we can solve this part independently by much simpler method, by using the same logic what I told you, that when the ball is released, it will move down on a curvilinear path, but thread tension will keep on pulling the sleeve towards left. So till the thread tension will pull the sleeve will accelerate, the speed will increase till the moment when thread become vertical. So when thread become vertical, velocity of the sleeve will be maximum. So we get this idea. We call it more preferred method. Because why I'm saying this more preferred method? Because it is simpler. Again, if the B part was asked independently, you had to follow such kind of approach. The leftward horizontal component of the tensile force of the thread accelerates the sleeve towards the left. Therefore, speed of the sleeve will keep on increasing till this component vanishes. That is, thread becomes vertical. Now, what we proceed earlier, denoting velocity of the sleeve and the block relative to the ground by u and v, because here we are not actually when the thread becomes vertical, direction of velocity of the ball is also known and direction of velocity of sleeve is also known. So we have only two unknowns, so we can use directly velocity of the ball with respect to ground. So here we have this vertical. So this velocity u of the sleeve is with respect to ground as it was earlier, and please take care, this velocity v is now with respect to ground because we are not superimposing this here. Now we can use conservation of momentum in horizontal direction, because we can see from here also that on the system there is no external force in the horizontal direction. Conservation of horizontal component of momentum. Summation p ix is equal to summation p final x. Let us substitute value. This was 0. It will be minus capital mu plus small mv. So mu is equal to small mv. That is simple equation. Work energy theorem on the system. For this, we know the total work done by all the external forces. Only gravity force on the ball, that is weight of the ball, is doing work. So it will be mg into displacement of the ball in vertical direction, small mgl. And all other external forces are not doing any work. And all the internal forces, there are two tension of this thing, their total work done is also 0. And final kinetic energy is kinetic energy of the sleeve, so half capital M into U square, and kinetic of the ball half small m into v square. Please keep in mind here we have taken v with respect to ground, and final kinetic energy we have obtained here. Initial kinetic energy system was 0, so let us substitute these values here in work energy theorem. Summation w external plus summation w internal is equal to summation k final minus summation k initial. So for this, what we have, mgl is equal to half mu square plus half mv square. Now just we can substitute v from here to this equation. What we get from the above two equations, we get u is equal to u max, that is 2m square gl upon m plus m into m, the same result we obtained here. So this method we have I have written here. If this part was asked independently, normally if you see your textbook, the velocity of sleeve we have to find when thread becomes vertical, or maximum velocity of sleeve. But here we have obtained in part A what is velocity of sleeve when thread has turned through angle theta. But in this part, in this first method, we have made use of the expression obtained earlier. Now let us see what is part C of the problem. Find tensile force in the thread when the thread has turned through an angle theta. So when thread is making angle theta, at that time we have to find what is the tensile force in the thread. How we'll proceed here? The ball moves on a circular path with respect to the sleeve. Radius of the circular path is equal to the length of the thread. This idea suggests us to apply Newton's law from a reference frame attached with the sleeve. One more thing. Actually, when thread is making some angle theta, at that time, the tensile force of the thread is pulling the sleeve towards left, so sleeve has acceleration. And any reference frame attached to sleeve will be a non-inertial frame. So we have to account for the pseudo force also. So let's see, the frame attached with the sleeve is a non-inertial frame. Thus, corresponding pseudo force must be taken into account. And what will that pseudo force? Suppose we assume tension T. So horizontal component tension T will be T cos theta, and upon capital M will be acceleration. So the corresponding pseudo force on the ball will be mass of the ball into T cos theta upon mass of sleeve towards right. So let's apply Newton's law and we show this force in the force diagram. NLM for the sleeve in the ground frame. So we are using NLM for the sleeve on the ground frame. This we are using to find acceleration of sleeve, what I have told you earlier. So that is sleeve mg T at angle theta and normal direction is equal to capital M into A. Now here there is no need to write equation in the vertical direction, only horizontal direction. So what we have, that is a summation fx is equal to max. So T cos theta is equal to capital Ma. So here A is equal to T cos theta upon capital M. This acceleration we will be in need to write the pseudo force. So let us write equation number 5. NLM for the ball in the non-inertial frame attached with the sleeve. So in this frame, we have to apply pseudo force corresponding to that acceleration, and this acceleration is towards left. So pseudo force on the ball will be towards right. So that is the ball, weight mg. That is here the thread will be in the perpendicular to this direction. So this way, tension T, and perpendicular to thread this dash line, and mg, this angle will be theta because this angle will be theta here. So you can see by geometry this angle will be theta. Again, that is what? Pseudo force small m into A, and this will also make angle theta. That will be equal to, because the ball is in circular motion, it has velocity. So normal component acceleration and tangential component of acceleration. So we have shown both the effective forces. So that is what we know, kinetic diagram. And there is also a kinetic diagram. This is FBD. Here strictly this we cannot call the free body diagram. Actually, free body diagram is defined for the Newton's law in inertial frame. So whenever we depict the pseudo force, this diagram is not called free body diagram, but we can say here free body diagram in non-inertial frame. But strictly when we call free body diagram, the free body diagram includes only physical forces. Now we can write the component of Newton's law or force balance along the normal axis. So here the normal direction, tangent direction. So summation Fn Rp, real and pseudo, is equal to Man. So what it here, T minus this mg sine theta plus Ma cos theta is equal to mv square by L. Now we substitute the values, value of A and value of V. So let us call equation number 6. We write the relevant equation. A was we have obtained in equation number 5. This is the T cos theta by M, and equation number 6, this one we have written earlier. Refer the equation 2 for the conservation of the horizontal component of momentum of the system, and equation 4 for the velocity of the sleeve obtained in the part A. So what these equations are? This is conservation momentum, m plus mu is equal to mv sine theta, and speed v we have obtained earlier, u is equal to m square gl sine cube theta upon m plus m cos square theta. say equation number 4. These 2 and 4 we have done earlier. Why I am writing this one? Because with these two equations, we'll find value of v from here. So velocity v of the ball relative to the sleeve from the equation 2 and 4, because we have to find velocity of ball relative to sleeve v. So from here we can find v. V is equal to, that is a simple algebraic manipulation. You can verify it. So that is v is equal to under root 2 m plus m in bracket gl sine cube theta upon capital M plus small m cos square theta. Now we substitute this value of v here, a here, and we can find tensile force. Let us call equation number 7. Substituting a from equation 5 and v from equation 7 into equation 6, we get t minus mg sine theta into m t cos theta upon m into cos theta, because for a we have written t cos theta by m here. Now we have to substitute for v. So we get here equal to m by l. V square means we have to put this expression which is under the square root. So we get this 2m plus m gl sine cube theta upon capital M plus small m cos square theta. Now we can solve this equation. I am leaving this algebraic solution to you. I am writing the final expression. So t is equal to mg sine theta capital M plus small m plus m plus 2m sine square theta upon m plus m cos square theta whole square. So that is a tension in the thread when it has turned through angle theta. So now let us come on the next part. D. Find tensile force in the thread when the thread becomes vertical. Again, this we can solve by two ways. First one, the expression what we obtain, substitute angle theta equal to 90 if this D part is asked after the C part, and if the D part were asked indirectly or independently, or only D part were asked, so we have used some other method. So what we do here again, refer the result obtained in the previous part. What the result? T was mg sine theta, that is m plus m plus under bracket m plus 2m sine square theta upon m plus small m cos square theta whole square. Substituting theta equal to 90 degree in the above equation, what we get? The desired result. So T is equal to 3m plus 2m mg upon m. That is the tension in the thread when the thread is vertical. More preferred method. When the thread is vertical, we can use intuitive based idea. Again, at that time, velocity of the ball direction is known, so we have to find its magnitude only, and velocity of magnitude of thread, so we have two unknowns. Again, we know at this instant also the ball is in circular motion with respect to sleeve on the path of radius L. Referring the more preferred method of part B, we rewrite the momentum conservation equation and expression for velocity of the sleeve when the thread becomes vertical. What is mu is equal to mv. Here v is the velocity of the ball with respect to ground, and u max was u was u max 2m square gl upon m plus m into m, because when thread become vertical, u will become u max. That result we have obtained earlier. Now we have to find velocity of the ball with respect to sleeve, because here we have to apply Newton's law in the reference frame attached with the sleeve. So what we do here, velocity of the ball relative to the sleeve, that is vb slash s is equal to v plus u is equal to this. You can solve from here. Why v plus u? Because v and u are in opposite direction, so relative velocity will be their magnitude sum. So we obtain this here. Now we have to use Newton's law on the ball in the frame of reference attached with the sleeve. Let us call equation number 8 an LM for the ball in the non-inertial frame attached with the sleeve when the thread is vertical at that moment. So at this instant, velocity of the sleeve is maximum. In addition, the sleeve is in unidirectional motion. Therefore, the reference frame attached with the sleeve is an inertial frame. Why? Just this. At present, we have shown that thought that this frame should be non-inertial, as we have seen earlier in this previous part, because when thread was slant. But the moment when thread become vertical, at that moment velocity of sleeve will become maximum, so its acceleration will become 0. So at that moment reference frame of the sleeve will be an inertial frame, or we can call this a momentarily inertial frame. So there is no need to account for any pseudo force. So that is very important point here. So here T and mg, that's free body diagram equal to kinetic diagram. So what we have, mvb with respect to sleeve square by L. Now we substitute value in the equation for summation Fn is equal to Man. So T minus mg is equal to mvbs square by L, and this value we substitute here and we get T. So from equation 8 and 9 we get T is equal to the same expression what we obtained. So that was part D. Now here this is a very important idea. Sometimes a reference frame may become inertial for a moment, and we can call later this kind of reference frame as momentarily inertial frame. So at this instant there is no need of applying any pseudo force. Let us see what is part E. Find displacements of the sleeve when the thread has turned through an angle theta. So at that time we have to find how much the sleeve has displaced. So let us first think the kinematics, how the displacements are there. Consider the system configurations at the initial instant t equal to 0 and at the instant t is equal to when the thread has turned through angle theta. So at these instants we just compare the system. So initially system was like that, and at time t equal to the system will be like that. So thread has turned through angle theta. So horizontal separation between the sleeve and the ball will be L cos theta. And we denote that the sleeve has shifted here by delta xs and the ball has shifted horizontally by delta xb. We consider only horizontal displacements. So that is the separation between ball and sleeve L cos theta. That is displacement of sleeve delta xs. That is displacement of the ball delta xb. So from this configuration what we can write here, delta xs plus L cos theta plus delta xb is equal to L. The geometry suggests what delta xs plus delta xb is equal to L1 minus cos theta. That is alternative way of writing that. What I suggest you, this plus this equal to that. So this plus this is equal to this minus that. So we have written this one. So let us call this equation number 10. Refer the momentum conservation equation 2 obtained in part A. What was? M plus mu is equal to mv sin theta. V sin theta is a horizontal component of velocity of the ball with respect to sleeve. So with respect to ground, it will be v sin theta minus u towards right. So we are writing this momentum conservation equation. We have written it earlier. So giving it the earlier number, the equation was number was 2. V sin theta is equal to m plus m by m into u. From here we can find v sin theta. The horizontal component of velocity of the ball relative to the ground, what will be? This will be v sin theta minus u. So how? Because that is velocity relative to the sleeve. So ground, it will be v sin theta minus u, and we can find it mu by m. Let us call equation number 11. Now we have obtained horizontal component of velocity of the ball with respect to ground, and horizontal component of velocity of sleeve we also know. From ideas of kinematics, what we can write here? Delta xs is equal to u dt, because this is the horizontal component or velocity of the sleeve that is totally horizontal with respect to ground. So displacement of sleeve will be integral 0 to tau u dt, and value of u we can substitute from here. So delta, and before substituting, let us write what will be delta xb. That will be integral vbx 0 tau. For vbx we put here. So what will we now? Employing equation 11, we get delta xb is equal to 0 tau mu by m. For this vbx we have substituted this. So m by m we can take outside integration. So what we have this, and from here you can see that is delta x's. So from this equation or this result we can find ratio of delta xb and delta x's. So delta x's by delta xb will be small m by capital M. Let's call equation number 12. Now see equation 10 and 12. That is now problem remaining only for ratio and proportion. So we have two quantities, the ratio is known and their sum is known. So we can write what is delta x's, ratio upon sum of ratio, m upon m plus m into their total, this. So delta x's we can write very easily from equation 10 and 12. Delta x's it will be m upon m plus m into L 1 minus cos theta. Actually, this problem, later when we study about center mass, at that time we'll solve this problem much easily with a very in single 1 or 2 steps. But what I suggest you, only learning the most suitable method to solve a problem is not learning physics. Actually, whatever method we have learned, we must be able to know the full potential of those methods. So here, this idea I have solved with this very elementary method. So as I have suggested you, this kind of situation we can greatly simplify by center mass. So let us document it. What? This idea will greatly be simplified with the help of concept of mass center. Now, today what we have taken several examples, and especially this last example, several parts. And we have seen so many intricacies, how momentum conservation, energy conservation, Newton's law, all these things can be applied in a single problem for different decisions. Actually, don't think that this problem is from momentum conservation. Actually, in a problem which has a lengthy solution, we have to take several decisions. And each and every decision is based on which method is applied there. So again, I revise what are the basis of selecting method to take a decision. Whenever you to describe or take decision, what is happening at a point of time, there is only way to use Newton's law. And when we have to correlate speed changes with space interval, we have to use work energy. And whenever we have to correlate velocity changes with time interval, we have to use impulse momentum. Again, whenever there is chance to use conservation momentum, use conservation momentum. And again, whenever some work and potential is asked, there is no way to use energy method. So today's talk, I'll just concluding remark, what was that? How to select different approaches for different decisions. Thanks for patient listening. We'll meet in the next class. In the next class, we discuss about collisions. Thanks. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.